Artificial intelligence can pass the bar exam, write flawless Python code, and draft a college-level essay in seconds. Yet, if you ask that same multi-billion parameter system to fold a t-shirt or pack a sandwich into a bag, it completely fails. AI pioneer Yann LeCun points out a gaping hole in modern machine learning. It lacks basic common sense and a working knowledge of physical reality. Large language models operate as massive pattern recognition engines. They predict the next logical token in a sequence of text based on statistics, but they do not simulate cause and effect. A system can output millions of words describing how gravity works without possessing any actual concept of space, depth, or the physical constraints that govern our world. Dr. Fei-Fei Li, a leading researcher in computer vision, suggests we can see this flaw by looking at the history of biological evolution. In the timeline of life on Earth, language is a highly recent development, emerging roughly 500,000 years ago. But over 540 million years ago, early organisms like trilobites began to process light. This ability ignited an evolutionary arms race. Physical perception built the foundational layer of intelligence across most species, a layer current machines bypass entirely. This missing piece is known as spatial intelligence, the capacity to understand 3D space and interact safely with a physical environment. In 2012, a massive dataset called ImageNet trained computers to recognize and categorize 2D photos. But placing a label on a flat image is a passive act. In nature, seeing is for doing. Perception exists so an organism can take physical action, requiring a deep understanding of geometry and depth. To bridge this gap, engineers are building systems known as world models. Programs like World Lab's Marble are designed to construct an internal mental picture of a given environment. This diagram illustrates a side-by-side comparison. Generative video tools create a flat grid of pixels that constantly shifts. World models, however, generate a permanently consistent, interactive 3D navigable space. By maintaining a stable geometric structure, the AI moves from generating media to actively simulating physical rules, allowing objects to be picked up, dropped, or moved within that space. Training these models introduces a massive hurdle, the reality bottleneck. Engineers can scrape the entire internet for clean text to train chatbots, but high-quality data of physical interaction in 3D and 4D is messy, complex, and incredibly scarce. The solution involves a hybrid data strategy, relying heavily on generating infinite, highly varied synthetic 3D environments to feed the algorithms. These simulated rooms act as flight simulators for AI agents. They provide a safe, scalable arena where machines can test actions and experience consequences without breaking physical hardware. We have seen this brute force approach before. Early self-driving car projects spent decades outfitting vehicles with sensors to collect physical data. Training embodied machines requires the same long-term investment. This creates a compounding flywheel effect. As simulated spaces become more accurate, physical robots learn faster, and their real-world interactions feed better data back into the original models. We are already seeing practical applications of this technology today. Game designers, VFX artists, and architects use spatial models to construct and navigate complex digital layouts. Clinical researchers use these models to quickly generate personalized, immersive 3D environments. This allows them to create specific, triggering settings for patients undergoing OCD exposure therapy. The ultimate target, however, is generalized robotics. The goal is to equip machines with an innate understanding of cause, effect, and geometry so they can operate safely in human spaces. Dr. Li's lab recently demonstrated a precise robotic arm preparing a Japanese sukiyaki meal, controlled entirely by a human user's brainwaves. By mastering spatial intelligence, machines are finally breaking out of the chatbot window. They are evolving from conversational interfaces into active, capable participants navigating our physical reality.